Yeah, hi everyone. This is Dr. S. Venkateswarlu, working as a professor of EC, IARE, Hyderabad. Yeah, today we will discussing about discrete Fourier transform applications and what are the importance of discrete Fourier transform (DFT) and some examples we will see. So here, many applications demand the processing of signal in frequency domain. You know that all importance. What do you call major applications are involved with the frequency domain. Okay, so in this, the analysis of signal frequency, periodicity, energy, power spectrum can be analyzed in frequency domain. We know that all time domain analysis, how they are using that domain, but this case, many applications demands the processing of signals in the frequency domain. The analysis of signal frequency, periodicity, energy, and power spectrum can be analyzed in frequency domain. Yeah, frequency analysis of the discrete time signal. This all are based on the discrete time signal, DTS, discrete time signal, or discrete time signals is usually and most conveniently performed on a digital signal processors. So that is the major application in the frequency analysis of DTS is usually the most conveniently performed on a DSP processor, digital signal processor. Now applications of DFT and or you can consider that discrete Fourier transform applications. So one is what you call spectral analysis and convolution of the signals. Okay. Next, partial differential equations, multiplication of the large integers. Okay. Sometimes the majority in image processing data compression and so on. Okay. Using this all analysis, time domain, frequency domain, and transform already we have verified. Okay. With this, the DFT, discrete Fourier transforms. The time domain signal samples to the frequency domain. Here it is. The time domain is where x-axis is the t, where y-axis is the amplitude. Okay, the signal is available. Apply the discrete Fourier transform. Okay, it is given to that frequency domain. This is all what you call in terms of the time domain. So given to that frequency domain, the x-axis is the frequency, y-axis what you call amplitude, the signal. Here it is signal is available in time domain, but in this case, while we are using given to this what you call frequency domain, we will expect the signal is in time domain only signal, but in a frequency domain, the signal spectrum will appear. Okay, so that's why the DFT, discrete Fourier transforms the time domain signal samples to the frequency domain components. Here the signals are so we have lot of signals. So naturally, we can see we are scanning something, smaller signals. Here, signal or the signal is identified of the types of the transform. What are the examples? Or maybe waveform, how it is expected waveform. For this case, the signal is ready. So we know that all signals, one is continuous and periodic. This is continuous and periodic. And continuous, periodic, and discrete and periodic, discrete and periodic. If you are using the continuous period, that is, we are using that relevant transform is what we call Fourier series. For the output response, the waveform we will expect the sine wave. Yeah, continuous and periodic Fourier series, we will expect that all response. Okay, discrete and periodic and Fourier, that transform this Fourier series, we will expect that our desirability. Discrete and what you call periodic, the Fourier, that type of the transform is the Fourier series, we will expect that all waveform desirable waveforms. Okay, so with this, the DFT has a linear transformation. So why is the linear transformation? The discrete Fourier transform, it is followed by what do you call x of k. X of k, where x of k is equal to the summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi n kn, where k is ready to substitute k equal to 0, 1, 2, 3 and so on up to n minus 1. Okay, so here where x of k is equal to the summation x equal to 0 to n capital N minus 1 x of n with the twiddle factor. That means these are all, you know that. So these are all nothing but the twiddle factor. It is followed by wn k, for k equal to 0, 1, 2, 3 and so on n minus 1. Okay, where let the twiddle factor wn is equal to e power minus j 2 pi by capital N is called twiddle factor, where this one is twiddle factor. Okay, now so we will ready to write the twiddle factor in terms of that given x of k. That x of k is given here, x of k. The k is ready to substitute k equal to 0, k equal to 1, k equal to 2, k equal to 3, k equal to 4 and so on. Okay, for this, by using this all twiddle factor, all this side all are ones, this side also all are ones. Okay, this side all are 1. First one is the w square, w cube and so on, wn minus 1. Next line w square and w power 6, w power n minus 2. Next, yeah, w3 power 3, w power 4 and 9. Okay, and so on, w power n minus 3. Like this, that w and so on, go on using that all this all values according to this. Next, wn n minus 1, n is 2 of n minus 1, w3 of n minus 1 and so on. W of, here it is n is ready to substitute, but here that n is n minus 1 with n minus 1 into n minus 1. So product this one into x of 0, x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of n minus 1. Okay, like that, should write that all x of k. Okay, so here it is, somewhat it is involved periodicity property of what you call the twiddle factor. So where wn is equal to e power j 2 pi by capital N. Let us consider for n is equal to, here this n value is equal to 8. That means w8 equal to e power minus j 2 pi by 8. 8 into what do you call this one, where x of k is equal to the summation k x equal to 0 to n minus 1, x of n wn k, for k equal to 0, 1, 2, 3 and so on up to n minus 1. Where this one is the twiddle factor, if it is n is equal to, since here it is, here capital N, you know, capital N is equal to 8. So the w8 kn is equal to e power minus pi by 4 into kn. Okay, so like here, we want to create the table. Consider this is the example or problem 1. Create the table if kn equal to 0, 1, 2, 3, 4 and 5 up to 7, 8, 9, 10, 11. So what is the result with effect on magnitude and phase response? So in depth of this, while you are using this all under discrete Fourier transform with the periodicity property of the wn. So what is the, using this all example, create the table if kn is equal to 0, 1, 2 up to 11. What are the results with the effect on magnitude and phase? Like this, we have to verify where kn value, okay, this kn value is given, kn is equal to 0, 1, 2, 3, 4, 5 and so on up to here. Kn is equal to 0, 1, 2, 3 up to 11 as per the given data. Where according to the twiddle factor Wnk. Okay. So n is given here, capital N is 8. That's why W8 Kn is equal to e power minus pi by 4 into Kn. Okay. Because of, we know that what you call e power. So this value according to this 2 pi by capital N. That means here I have to use that where N is 8. Okay. K, what you call Kn. Okay, using this, the e power, already say Wkn is equal to e power minus pi by 4 into Kn. Okay, according to this, 880, e power 0. So e power 0, okay, we know that 1. So that means the phase here, magnitude is 1, the phase is 0, and so on. Weighting function 8, where it is the m1, n is, okay, e power minus j pi by 4 into 1 e power minus j pi by 4. Okay, so here we are going to verify that the magnitude and phase. Magnitude and phase. Magnitude is 1, phase is minus, what do you call, minus pi by 4. Okay, next, where that Wn is 8, we know, what you call Kn is 2, that is equal to e power minus j pi by 2 into 2 e power minus pi by 2. That means 2 ones and 2 twos. That means e power minus j into pi by 2. So according to this, the magnitude is 1, phase is minus pi by 2, and so on. Go on using this all, where Kn is equal to 3, where Kn equal to 4, Kn equal to 5, like this. But all are the magnitude is 1, the phase will be varies. The phase values varies. So finally that the Kn is equal to 11, W8 Kn is equal to 11, W8 11 is equal to e power minus j pi by 4, okay, equal to e power minus j 2 pi plus 3 pi by 4. That means W8 11 is W8 3. So like this, you have to create the table if Kn value is given. So the resultant we will expect the magnitude and phase values. Using this all formula, we have to write that all piece of code using the MATLAB. We will verify the graphically. Okay, like this. Next year, yeah, figure periodicity of the Wn and its values. Periodicity, using this property, periodicity of the weighting function Wn and its values. Okay, yeah, initially we know that all for this case real value and what you call imaginary value. Here this is the real part, this one is imaginary part. You know, according to this real part and imaginary part, we will verify that all how many what you call weighting functions Wn and its values. Yeah, initially that this case we have to concentrate on, this is the origin from here to here, we have to split like this. Okay, so this value is what you call, this is the origin. You can consider where this here it is mentioned real part of Wn, real part of this W1 is W8 0. Okay, in this case W0, because of since that capital N we know where capital N is equal to that, as per this previous example, capital N is given 8, W80. That means where W80 equal to, okay, W80 equal to what you call 1. Okay, so here W88, okay, this is W80, this point is W80, next one is this direction W81, okay, W81 and W82, because of This kn value is 0, 0, 1, 2, and what do you call 3, okay, 4, 5, okay, 6, 7, like this. Okay, here we have to observe this all imaginary part of the Wn and real part of Wn. Here it is W80, where this W80 is equal to what you call W8 is both are equal to 1. This is one aspect. Coming to the next point here, W81 is equal to W80. That means 1 by square root of 2 root 2 minus j into 1 by root 2. Okay, next coming to this W82 is equal to W810. Okay, so here it is minus j. Similarly, W8 3 and W812, so it's also equal to minus 1 by root 2 minus j into 1 by root 2. Similarly, that W8 4, W812. Okay, this is minus 1. Here this value is minus 1. Okay, and W8 7 and W8 13 is equal to minus 1 by square root of root 2 plus j into 1 by root 2. Like this, we have to verify the periodicity of the weighting function or fiddle factor Wn and its values we have to identify. Because of we have to compute that discrete Fourier transform. If it is, we will verify that efficient computation. That we require this periodicity of the what you call weighting function or maybe fiddle factor, and its values are like this. Okay, it is very much useful for the efficient computations. How they are calculating the DFT or IDFT. That time we have to follow this periodicity of the weighting function or fiddle factor and its values. Okay, so like this. So one thing you have to verify with the help of the periodicity of the weighting function or fiddle factor. So all values we will verify the periodicity of this weighting function with this what we call that weighting function. Okay, that how it is where the two similar values are equal or not, we will verify the periodicity of weighting fiddle factor and its values. Here, so periodicity of Wn and its values are here. It is somewhat it is identified W40. But here it is how many? Maximum is 1. Here it is 1, 0, 1. Here it is 2, isn't it? Here it is 2, 3, 4, 5, and 6, 7. Total is 8. Now the figure, this figure right side diagram, periodicity of the Wn and its values. The origin is same. Here the values are that real part of the Wn and imaginary part of this Wn. So initially W4 where n is equal to here that n is equal to since that capital N is equal to 4. Okay, but this case the since the capital N is equal to 8. How many 8 here? 0, 1, 2, 3, 4, 5, 6, 7 up to 0 means that is 8. But this case 0, 1, 2, 3. Okay, maximum is we will try to verify that. Here it is W. Okay, N is 4, W4 equal to 0 is equal to 1, W4 equal to 4, 4 and 8. All are same. That means N is equal to here it is. From this point, due to this point, we will try to verify like the fiddle factor N is equal to 4, Kn is equal to 0 is equal to one more equivalence. Next, the W4 what do you call and Kn is equal to 4 is equal to W4, that what you call Kn is equal to 8. All are equal. The value, equal value is 1. Okay, but here also 8, 8, 8 and so on, here also 1. Similarly, this case, if you are using this one, what about this case? This case is, so how it is equivalence of these two values. But, this case is ready to verify. How we are verifying that a weighting fiddle factor W4, where capital N is equal to 4, the Kn value equal to 1 is equal to the total factor Wn, N is 4, here 5 values, so Kn is equal to 5 is equal to what you call W4, Kn is equal to 9. All are we are right to calculate this value is minus j according to total factor. So this is this value. Next, coming to this third value, here where this W4 2 is equal to W4 6, W4 10, so the value is minus 1. Similarly, W4 3 is equal to j is equal to W4 7 is equal to what you call W4 11. This value and this value is same to what you call that value is j. Okay, if n is equal to 4, right side will try to verify. If capital N is equal to 8, left side will verify. But in terms of that, the real part of the Wn and the imaginary part of these values are required for implementing our DSP, what we call DSP related DFT, Discrete Fourier transform of applications. Some problems we solve by using this all periodicity of Wn and its values with the capital N is equal to 8, capital N is equal to 4. Okay, next DFT, some formulas, here it is. So this shows that development of the DFT formulas were here, where x, here it is, we know this one, where x of t and t versus x of t, this is the origin. We will expect this waveform. This is nothing but the portion of the signal is used for DFT and the spectrum. Okay, like this. This is the what you call, this portion of the signal is used for discrete Fourier transform and spectrum calculation. Okay, the calculation part, if the n value is like this, so that origin is 0, here initially x of 0, x of 1 and up to x of n, this width is n, so from here x of n plus 1 is equal to x of n, here this value. Next, x of n is equal to x of 0. Like this, the portion of the signal is used for the DFT and spectrum calculation. We have to follow this n versus, where n versus x of n. Okay, so now after this area, we have to verify that n versus x of n. Initially, that origin is 0, x of 0 here, x of 1, okay, x of 2, x of 3, x of 4, 5 and so on. These are all x of n minus 1, x of n minus 1. So that means where x of n is, we are having that x of n, that n value ready to substitute, n is equal to 0, n is equal to 1, n is equal to 3, n is equal to 4, where n is equal to 5 and so on, n minus 1. Say for example, n is given, previous example, n is equal to 8 or 4. Based on that, 8 minus 1, here 8 minus 1, it is 7, 4 minus 1, what do you call? 3. So this value is given to the DFT, discrete Fourier transform, where the t is equal to n into t. We will expect that all DFT. Input signal is x of n, output response is x of k with the help of the DFT, discrete Fourier transform, where x of k is equal to n into ck, k value ready to substitute, k equal to 0, k equal to 1, k equal to 2, k equal to 3, k equal to 4, and n minus 1. You have to verify that all the spectrum, the frequency value f equal to what do you call k into del f. If you want to calculate the delta f, del f is equal to fs by capital N. Sampling frequency by that what you call number of what you call capital N. Okay, like this. Finally, that x of k ready to analyze. Where x of k is equal to the summation k equal to 0 to n minus 1, x of n, that twiddle factor wn k, capital N and power and k, for k equal to 0, 1, 2, 3 up to n minus 1. Okay, like given sequence x of 0, x of n, 0 less than n minus 1 or n1, its DFT is defined like x of k is equal to the summation n is equal to 0 to n minus 1 into x of n e power minus j 2 pi kn by capital N. It's also equal to the summation n is equal to 0 to n minus 1 x of n with the twiddle factor wn kn. The k value ready to substitute k for k equal to 0, k equal to 1, k equal to 2, k equal to 3, k equal to 4, k equal to 5 and n minus 1. Okay, like this, where the factor wn called the twiddle factor. We know that is defined as what you call, right, to define that what you call that twiddle factor. After that, what are the inverse DFT, how we will write it to evaluate, how we are defined. So for this case, where twiddle factor is wn is equal to e power j 2 pi by capital N. It is also equal to cos of 2 pi by capital N minus this is sine 2 pi by n. It is very much useful for computing your twiddle factor with the help of what you call DFT, discrete Fourier transform. So coming to this inverse discrete Fourier transform. That means here it is right to calculate. This is the DFT, discrete Fourier transform. There is a what you call inverse of this x of n. That means here where x of n is equal to 1 by capital N into summation k equal to 0 to n minus 1 into DFT x of k into what you call e power j 2 pi. Here this case, okay, yeah, if you want to measure, you want to determine that DFT, that twiddle factor e power minus j 2 pi k n by capital N. But this case, it is the inverse now. X of k into e power j, but previously it is minus j. Here it is plus e power j 2 pi k n by what you call capital N. It is also equal to 1 by n. Okay, the summation k equal to 0. What about the DFT where n is equal to 0 in the DFT? Inverse DFT, I inverse discrete Fourier transform. You want to evaluate, right, to calculate, compute this IDFT. Is also equal to that 1 by n, the summation k equal to 0 to n minus 1 and x of k, that is DFT, into e power, previously this is minus j, here it is e power j plus j 2 pi k n by capital N. So here using this is also equal to 1 by n, the summation k equal to 0 to n minus 1, x of k, that is DFT, into the twiddle factor wn minus kn for n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, so on, n minus 1. Like this, we are right to define both what you call discrete Fourier transform and IDFT for verifying our applications. Okay, now DFT analysis and synthesis. The DFT transform, discrete Fourier transform, it is followed by x of k. X of k is equal to the summation n is equal to 0 to n minus 1, x of n and e power minus j 2 pi k n by capital N. This is analysis equation. And coming to synthesis, where it is DFT. IDFT, x of n is equal to 1 by n, the summation k equal to 0 to n minus 1, x of k. This is DFT. Here it is IDFT. IDFT, this is DFT. Okay, into e power j 2 pi k n by capital N. This is the synthesis. Analysis part and synthesis part. Okay, so this all the Fourier transform of discrete Fourier transform of transform. Okay, so alternative formulas where x of k, this is the DFT, where x of k is followed by DFT discrete Fourier transform is equal to the summation n is equal to 0 to n minus 1 x of n, the Tudel factor w k n. So where w is equal to, we know this, e power minus j 2 pi by capital N. The x of n is equal to, summarize 1 by n, the summation k equal to 0 to n minus 1, the x of k, the Tudel factor w minus kn. This is the alternative formulas for evaluating or computing, or we will expect that efficient computing while you are using DFT discrete Fourier transform analysis of the synthesis. Okay, now x of k is equal to, it is the DFT formula, we know that using this previous formula. Okay, so now schematic representation of the DFT. So we will apply in the application level, we will compute that efficient or normal cases. We have to follow this all, that DFT. The DFT formula we know, discrete Fourier transform formula. So where in terms of the schematic representation of the DFT, like graphically, here this is the summation. So here it is x of 0, then the Tudel factor is wk equal to 1, given to that summation, we will expect x of k, x of n minus 1, go on using the x of 0, 1, 2, that x of 0, okay, k equal to 0, 1, 2, 3 and so on, x of n with the Tudel factor wk of n. So, using this summation, we will expect that DFT discrete Fourier transform. This is the representation, left side is the mathematical expressions, where right side is the schematic representation of discrete Fourier transform. Now with the help of this x of k plus n, x of k plus n, x of k we know, but here it is added the x of k plus n. Summation n is equal to 0 to n minus 1, x of n into e power minus j 2 pi into k plus capital N into what you call n by capital N, like this. So where x of k plus n is, we will expect that what you call x of k. So where this value is, where x of k plus capital N is equal to x of k into e power j 2 pi n is equal to x of k. This is the DFT spectrum. X of k is periodic. With period n, recall that discrete time Fourier transform spectrum is periodic as well as, but with the period of 2 pi. This you can analyze if x of k plus n. Okay. So we will see that formula like in some examples of problems. Verify Parshall's theorem of the sequence x of n is equal to 1 power n by 4 e of n. Okay, here under this is your relevant solution. The summation minus infinity plus infinity x of n square is equal to 1 by 2 pi integral minus pi 2 plus pi x1 of e power j omega naught square into d omega. Okay, simplify this one, where LHS is equal to the summation minus infinity to plus infinity x1 of n naught square is equal to summation minus infinity to plus infinity x of n to x of convert this n. It means the summation the summation where minus infinity to plus infinity, okay, x1 of n, okay, not square is equal to, right, to analyze. Okay, so here in this case, after simplifying this, where this value, where LHS value is equal to the summation minus infinity to plus infinity, okay, 1 by 4 power, what do you call, 2 n into u of n according to given data. So I have to verify that this 1 by what do you call, 1 by 1 minus 1 by 16. So after simplifying this, okay, that means 16, that is 16 by 15, okay, like this. Now come to the RHS, where x into e power j omega 1 by that value 1 minus 1 by 4 into e power j omega is equal to 1 by 1 minus 0.25 cos omega plus j 0.25 sin omega. Like this, we are right to calculate the x of e power j omega into x convert e power j omega. Like this, we are right to verify that 16 by 15. Okay. So like this, we are right to verify. We can see that LHS is equal to RHS. Next example, compare the NDFT. These are the applications while you are using. We are learning that all DFT, discrete Fourier transform. Yeah, here in this case, second example, compare the endpoint DFT of x of n is equal to 3 into delta of n. So from this, and we were right to evaluate the solution. We know that x of k, this is the exact DFT. DFT formula is this, since this is the formula of DFT, discrete Fourier transform is equal to x of k is equal to summation n is equal to 0 to n minus 1 x of n and e power j, you know that, since that e power, okay, minus j 2 pi n k or k n by capital N. Here in this case, the n is equal to 0 to n minus 1 into 3 delta of n into e power j 2 pi n k by n. So here, after simplifying this, 3 into delta of 0 into e power 0 equal to 1. Here it is 1, where x of k is equal to 3, 0 less than or equal to k less than n minus 1. This is the expected result. If you were to compute that endpoint DFT of x of n is equal to 3 into delta of n. Okay, compute the endpoint DFT of the x of n is equal to 7 of n and n minus n naught. So one more example, compute, where the compute, here it is example number 3. Compute the endpoint DFT of the x of n is equal to 7 of n minus n naught. This is the endpoint DFT is given. So under this of their computing, we know that the formula of DFT, x of k is equal to this value. X of k is equal to, what do you call, the summation equal to 0 to n minus 1 x of n to e power, what do you call, e power minus j 2 pi kn by capital N. Substituting these values of xn, they have to simplify this. Summation n is equal to 0 to n minus 1, 7 into delta of n minus, what do you call, n minus, okay, n minus n naught e power minus j 2 pi kn by n. Okay, here e power k into j 4 pi by kn by n. Like this, we have to evaluate this all problems related things. Easily can evaluate. Okay, next solution, we have to verify that. So it is various DFTs. Okay.
Like, share and subscribe. Hit the bell icon for more updates.